want you to run yeah, I don't think it's on here, but run docker compose pull. So if you're familiar with Docker, you probably know what I mean. So it's gonna pull the pre-built image to save some time. So docker compose pull, and oh yeah, there you go. Docker compose pull to download pre-built containers, save you some time, and I'll see you back at 50. So I hope all of you guys downloaded our example, and so you can try running our examples. I believe the README instructions are inside. So so our demo actually doesn't have the screen running the actual program. We're gonna explain what each pieces of code inside mean. So I expect you to run and try our programs while I explain what they do. All right, so the first example is the secure password manager. So this is actually a student's first SGX program, and it's in fact not a very good, not a well-designed program, but I took it as an example because it shows us so many different aspects about programming in SGX. So the program tries to secure internet account passwords into SGX. So kind of like programs like 1Password and things like that. So this is an insecure program, as we're gonna see at the end, but it's still very educational because it shows how one can go wrong with the SGX security model design. So to build and run, you can enter that directory and configure, build, run. Just run the 3 scripts in order. All right, so this is what the program does. So the program gets the master password from the user, so you get it as a console input. So the SGX will load the saved password storage, which is encrypted. And then if the master password matches, then it's gonna send the plain text password over to the website that you're trying to log into. So this is actually not functional, but it's more like an example that shows how programs like 1Password can be implemented using SGX. So one of the features that are used in this example is secure file storage. So this program uses the SGX's key generation feature. So there's a dedicated instruction for that added by the SGX extension. So the instruction is called eGetKey. So if you do eGetKey, usually you won't call that instruction directly. It's more like you call the API that does that. It'll generate the ephemeral key from the root key that we explained earlier. So it's gonna generate the key, and it's a random key that you can use to store encrypted data, store a sensitive data, and save to a persistent storage such as SSD, hard drive, or memory. What's cool about this is that even though the key is random, the enclave can decrypt the file inside SGX. So the key is random, but the encrypted content can only be decrypted inside SGX. So another thing that goes into the generation of the key is the hash of your program itself. So the SGX hardware will measure the hash of your program and then use that to generate the key that is unique to your program. So that's how we use the secure file storage in SGX. So if you take a look at our source code example, you're gonna see a function called seal, and it's just a simple API call to the SGX SDK. The second facility that we're using is the secure communication inside the enclave. So as you can see, the student included a TLS library, the wolfSSL library inside SGX. So the SGX program is linked with the wolfSSL library. So the program established the TLS channel with the server inside SGX, meaning the session key only stays inside SGX, and the untrusted program components cannot see the encrypted channel. So this is how this is an example of establishing a TLS inside SGX. So looks like our student used CMake as the build system instead of the makefile, because makefile with SGX tend to be pretty ugly. So if you look at the directory structure, there's a directory called app. So that's the untrusted part. So that's going to be the main program component. And the directory called enclave has all the functions that performs secure operations, and all the functions that are defined in a file called enclave.c. So you can take a look at the source code. It's pretty short. It's very, very short, because most of the SSL functionalities come from wolfSSL, and most of the file encryption comes from SGX SDK. So there really isn't much in the C files here. So you can take a look at it. So this example shows the simplest form of SGX programming model. And we call it simply the splitting a program. So given a program, so in this model, it's up to the developer to identify what's the secret about this program and locate the functions that interact directly with the secret and separate it into an enclave. So the student decided to separate the following functionalities into trusted and untrusted. So as I explained, the secure file storage function went into SGX for obvious reasons, and TLS communication also. But as you can see, some parts are still left outside, such as the console UI, where you print the message onto the console to ask for the password. And also, if you check source code, there's socket creation that is happening in the untrusted territory. Anyone can guess why? Why are we creating the socket in the untrusted? Okay, we'll get to that soon. So yeah, so in this model, developer has to identify the secret and the functions that interact with it, and then I do the isolation and protection by themselves. And another thing that developer has to do is the developer has to design the eCall and OCall flow carefully between the untrusted and trusted interaction for the program to be safe. Okay, so if you are looking at the source code, you're gonna see a flow that looks like this. So the main calls eCall seal. Again, eCall is entering enclave, right? So you're calling enclave, please encrypt the file, and then enclave, and then the enclave mode calls a function called write buffer to file using OCall, right? So this is a common pattern in SGX programming that you're gonna see over and over, and this is what's very different from writing programs without SGX. So in this program, we're using that OCall.cpp to create proxies to libc and kernel system calls. So we said that system calls are not supported in SGX, right? It's not part of the trusted code base. So that's why you have to create proxies to be able to even save a file. So encryption happens on the enclave side, and the actual file operations have to happen in the untrusted territory. So this is the one of the essence of the SGX security model. So this minimizes the TCB of the enclave and also removes possibly dangerous direct communication with the kernel. Okay, to sum it up, in writing SGX programs, you define equals to enter trusted territory and then call trusted functions. And then you gotta use equals to proxy whatever the system service that you wanna use so that you can come out of enclave and eventually call the system calls. So this is very confusing to beginners who are writing their first program in SGX. It also is very annoying too. All right, so if you're looking at the directory tree, you're gonna find a file called enclave.edl. So EDL stands for enclave definition language. So this is the file that defines where you cross the border between the trusted and untrusted territories. So you have to explicitly define them to be able to cross the border. The reason is quite obvious, right? The entering and exiting enclave has to be only through the strictly controlled interface, and you as a developer is responsible for designing that flow. So a insecure equal or call might undermine the security of your program. So if you define the EDL file that looks something like this, so this is a format that is unique to the EDL. So it's basically a C header file with some more details. So you define the, if you see the top bracket, you define an enclave, and then you define the trusted components, which are equals. Then you define the untrusted, where you define all calls that can be called from the enclave. And one thing that is different from the normal C syntax is the text in bold. So you see out, it says out, and size is equal to some number, right? So when you're doing pass by reference in SGX programming, you have to specify the direction as well as the size. This is because SGX doesn't use the pointer directly. The compiler will automatically create code that copies the original data into the enclave memory, and then the enclave will use it. So imagine that you don't have that, and the enclave uses the pointer directly. All kinds of funny business can happen. So the enclave is executing using the pointer, and the untrusted program changes the memory contents. So that can cause all kinds of weird behavior. So that's why you have to specify the direction as well as the size. This is also the same for the kernel. If you have programming in, if you have experience in kernel programming, so kernel gets the argument, gets the pointer from the user program, but it's gonna make a copy before it does anything. So between different two privilege levels, different levels of security, you never use the pointer directly. All right, so I'm gonna explain why this program is ultimately insecure. So I guess this student started this project thinking to make something like one password, but he forgot that there's no secure I/O in SGX. I think he might have realized this as he was finishing up this program. So he didn't take that into account, meaning that the input coming from the user keyboard is not protected. So the kernel, malicious kernel, can install a keylogger and steal the keystrokes going into the enclave. So that's one failure made by the student. So, but this is surprisingly a very common misconception people have about SGX. So if you think you put something into SGX and people automatically think everything's gonna be fine, but it isn't. So you need to be careful. You need to have a close understanding on the SGX security model. You have to define the equals and equals carefully. And you also have to consider if you need secure I/O or not. And to further evaluate the security of this program, so imagine you have an account for Naver, Google, and iCampus in an array, right? You might run into side channels that we saw before, right? So imagine Naver, account information for Naver is one page, and Google is in another page, and so forth. So kernel can observe the memory access pattern and find out that the user is trying to access Naver or Google or whatnot. So the lesson here is that using SGX is not a remedy for everything. You have to set a clear security model and design your program accordingly. Okay, so another programming pattern that we see in this example is the use of ported libraries. So the student used the UlfSSL to use the SSL functionality here, right? So this is another very common programming pattern you see in the world of SGX software. So a lot of the software are ported as a whole. So for example, UlfSSL, OpenSSL, all these libraries are ported as a whole. So there was no conscious effort to make the TCB small, but they rather focused on maintaining the original API and original data structures. So we said that the less you trust, the more secure you become. But that doesn't always go like that in real practice. So it's much easier to just simply port the whole library and then use it as a whole. So this is another programming pattern presented by that example. And this is actually very quite common practice in SGX world. You're gonna see a lot of libraries ported to SGX as a whole on GitHub, for example. All right, so porting library should go something like this. So you wanna expose APIs that are meant to be called. So they need to be exposed in the form of equals, right? And then remember that we cannot call system calls or call libc functions that involve system calls. You have to make code in the enclave, use the all-call proxy to call simple functions like printf and socket. So this is a lot of work, right? This is a lot of repetitive work. And it is very easy for the developer to make mistake and make the library insecure. All right, so if you might be wondering how difficult is it to port programs and libraries to SGX, I would say it's a time-consuming task, but it's doable. I mean, if you put your time into it, you're gonna finish it eventually. But my students may say otherwise. It's not easy to actually set the security model and define all calls and unequals and verify if they maintain the confidentiality of the original library. So that's not an easy task. And my students had to suffer through many, many hours of porting stuff to SGX. All right, so this is sort of a solution to that problem that my students suffer from. So this example shows how to do SGX to perform dim learning. So it demonstrates the concept of using library operating system to deploy complex software. So using library OSs allow developer to use their unmodified program inside Enclave and also conveniently send their workload to the cloud. So library operating systems are being actively explored in the academia and as well as on GitHub. There are constantly incoming commits to the projects showing how many parties and developers are interested in the effort. So library operating systems try to bring operating system components into Enclave. So instead of directly calling the system call, you put some kind of emulation layer into the SGX, and your SGX programs interface with it. So that way, it's kind of like having a very small virtual machine, software virtual machine inside an Enclave. So that makes everything easier. So you can run unmodified programs inside SGX where all the operating system capabilities are there. For example, if you have to use malloc, you just use malloc. And that is emulated by the compatibility layer sitting below. So there are pros and cons of this example, of this approach. The good thing about this approach is that it actually becomes more secure in a way, because the risk of interfacing untrusted kernel is reduced. Because usually such library OS designs have some kind of dedicated interface to talk to the kernel. So instead of calling a rich set of system call functions, it will only call simple functions like read, write, and so forth. So since the interface is minimized, the complication that comes with the performing complex interactions with the kernel is actually minimized. But the downside is obvious, right? Because you're going to have a significantly bigger TCB, since now you have your high-level program that is written in possibly Python, Java, and you also have the library OS inside the Enclave. So you have a huge TCB, so it has pros and cons. But like I said, it is a highly sought-after approach that is being actively developed by the researchers as well as the dinosaur cloud service provider companies like Microsoft. So they're the one who are mainly interested in this approach, because it makes confidential computing and managing the workloads light years easier. Okay, so the library OS that we use for the example is called SGX LKL. So in SGX LKL, workloads are deployed in a disk image, which is going to be run inside the Docker eventually. So they pretty much automated everything about running unmodified applications inside SGX. So using the commands provided by them, you can create a disk image. You can also, they automate the remote attestation that we learned today. They're going to incorporate the key and code into your disk image automatically. And it'll also upload the workload to the cloud provider in disk image automatically. So this is the general flow of creating a workload disk image using SGX LKL. And I'm sure there's a description on this process inside the repo, so you can follow the steps to recreate the workload with SGX LKL. So SGX LKL, from our experience, the easiest library OS to deal with. And so right now, your computer may or may not have SGX. So we set it to run in simulation mode, meaning it operates just like the real hardware, but it's just that everything is simulated and you don't need the SGX capability. So the Docker image has everything pre-installed, as well as our program. And so we have two examples. If you look at the directory structure, we have hello world that you're probably not interested in, we have really interesting example that runs PyTorch unmodified inside SGX. So to use SGX LKL, you just need to be familiar with this commands to create the disk image and deploy them into the cloud. So the reason why we're introducing how to use this library OS is that not all of you are systems programmer, system security researcher, but you might be interested in incorporating the SGX functionality in your projects, right? So I think in most cases, using library OS such as this one will help you in the long run. It's not easy to actually learn how to use SGX SDK and take time to learn how to do the security model, OCall, equals, and everything. So for those of you who are not system security experts, this is probably the easiest way to deploy SGX-based services at this point. Okay, so Hello World is a simple program that just shows that this works. And the fun part is the PyTorch example that we have in the tutorial. So it runs the PyTorch example. It runs the example of training example using the Cypher 10. So the reason why we had to use Cypher 10 was because, can anybody guess? Why did we use such a small one? Memory limitation, right? 96 megabytes. So we had to use a small one. So this shows the current limitation of SGX. So if you want to do a huge training on a huge library, you're going to have to come up with some kind of workload splitting scheme so then you can run things in batches, which is not easy.
I have one question.
Yeah.
Actually, I think that training requires more computational resources, but testing requires less computational resources. So it means that maybe if we just train the data set on some untrusted device or model, but maybe after training the model, maybe we can just upload the pre-trained network model to Intel SGX model, and then maybe SGX just can be used for testing. Is this right?
Yes, I think that's a very good point. Even though training can be difficult to do with SGX, but doing inferences using a pre-trained model can be actually deployed as a service, even with the current memory limitation.
Okay.
Yeah. But I think many people might be interested in not having to buy 10 GPUs to train a model and buy a storage for terabytes of data. So that's when people want to use cloud services, and the current limitation of SGX is kind of impeding the adoption of confidential computing in cloud, in my opinion.
Okay. And also, I have an additional one question. Sorry. I think that probably here the threat model is to protect some sensitive image from untrusted server, right?
In this particular example, we're actually protecting, since we're protecting the whole program as a whole and deploying as a encrypted disk image, we're actually protecting both data and the
Code.
The result, which is the trained model.
Okay, but as you already mentioned, without secure I/O channel, how can it protect the confidentiality of input image?
Well, confidential secure I/O with, for example, GPU is not supported, but with the sealing facility that I explained, you can always encrypt the data and then save it into the storage and then bring it back to Enclave and decrypt it.
Okay.
So yeah, actually that's a really good point. So secure I/O with storage is possible in theory, but interfacing with, for example, computational devices such as GPU requires the active participation from the other end. All right, so moving on. Yeah, but it is not perfect. So according to my student, he had to remove OpenMP because of some compatibility issues. So library OSs are still new, and they're not guaranteed to provide 100% compatibility. But it is quite surprising to me, who has seen the first introduction of SGX, known it for many years, to see this finally happening, running unmodified programs in SGX. So if you have done Docker Compose pull, you probably have a pre-compiled image of SGX LKL example in your computer. And so this is just the steps involved in creating the image. So if you run the code using that exact command, you're gonna see the training phase and then inference phase in your computer. Is it working for everyone? So who else succeeded in running this? If you have an error message, then let me know. I can probably tell you right away. Okay, so I guess everyone's seeing this screen, I guess. So yeah, in summary, you can use SGX LKL or other library operating systems to deploy unmodified workloads to the cloud. And to be a little more specific, this is how you would run your own workload using SGX LKL. All right, so we covered 3 different programming models, right? So first is the manual way. Developer identifies secrets, split the program, and do everything manually. And the second example was the porting the library, which is a common practice in the SGX world, but a little bit insecure because it's not done with the small TCB in mind. So oftentimes the libraries are just simply ported without thinking about the TCB. So the whole OpenSSL library, which is well known for its Heartbleed vulnerability, runs as a whole inside an enclave. But developers do that because it's just simpler and easier. The last example we saw was the using library operating system, which is a very interesting approach from operating systems research perspective. You put everything inside enclave. So it's basically like a small operating system as a whole running inside enclave. But as you can probably tell, so in the beginning of this presentation, I said the less you trust, the more secure you become. But you're seeing the modern SGX programming practices actually going opposite, right? So another lesson we can learn from the demos we saw today, the more you trust, the easier your life as a developer become. It's much easier to run SGX programs using library operating systems. All right, so that's all I have today. I will be happy to take any questions, any topics for discussion.
Okay, thank you for presenting nice tutorial. Yep, it is really great to me. I have one question. Actually, I think that, as you already mentioned, it is quite difficult to port existing library into SGX-enabled library. So most people, most developer probably just try to use existing SGX-enabled library. In this case, how can you trust those library are really trustworthy and verified?
Uh,
I mean,
there's no safety net. You just clone from GitHub and you just use it. There are some libraries that are ported by Intel. I don't know if that gives any more trust, but in many cases, many SGX papers make their work open source, and you often just steal from their example, and so you steal from someone else, and someone else steal from you. So that's how the GitHub.
yeah, my question is that in the view of a developer, probably we need to trust you because your code is really trustworthy. But maybe, we don't know, maybe you installed some backdoor into your code. How can you trust this?
I guess the answer is you cannot. Actually, that brings up a really good point because people think using Enclave is just more secure for some reason, but it isn't. If you start loading insecure software inside the Enclave just becomes another normal user mode. So yeah, it is, in my opinion, it is important to keep the TCB low and maybe do something else, maybe try something else than the library OS approach. But I think that's the industry is the direction that the industry is pushing because they wanna gather developers on their platform.
Okay, I see. Also, I have another question. I think that maybe suppose that we developed SGX-enabled password manager. It sounds really good, but in the view of a user, how can I identify whether this is SGX-enabled password manager? Because maybe some malicious developer can develop some malicious password manager mimicking SGX-enabled password manager, but user cannot distinguish it. Yeah.
Right. It's a really good point. That example is just for the sake of example. So I think the password manager example actually has very little use in real world. I think the real value of the SGX Enclave is the cloud computing. You want to see that your program is inside SGX and you want to verify it.
I see. But I think that it seems a challenging issue. Yep.
Right.
Thank you for the nice talk, and I have also one question. So I understand that there is, trusted part and untrusted part, but they should be done by the developer. This means if the developer failed to have a clear boundary between trusted zone and untrusted zone, does that mean it depends on the developer when they design?
Yes, I think that's also true for any trusted execution programming. So it's ultimately up to the developer to secure. So I guess it starts with identifying what to secure and identifying how it can be leaked. It's not just about simple function calls. I mean, there can be side channels and so many other ways that your confidentiality can be broken. So yes, the developer's capability is also important for the secure use of enclaves.
Okay. So that means if the developer has a kind of bad security practice, then it's kind of similar to what we had before. Okay, thank you.
Right.
Thank you for your nice talk. I have a question about the scalability of the SGX. So when considering the many core system and when you consider the 3,000 container are executing this one CPU, so what is your opinion when designing the next generation SGX regarding the scalability or the multi-core, multi-container system?
Are you implying the possibility of
Yes.
side channels inside a
Yes,
CPU?
one of
Okay.
the question is about that.
That's actually very difficult problems that a lot of researchers are working on. So, so when we saw the boom of the side channel attacks, for example, Meltdown, Spectre, and all the variants of attacks, a lot of papers were about applying those techniques to SGX. So some of them work, some of them don't. It really depends on how Intel implemented the internal hardware intrinsics of the SGX technology. So there's no general solution for that. I guess it's just us security researchers to find out. So if Intel has forgotten to flush out certain cache contents before making the switch, then it's a vulnerability. If Intel didn't forget, then it's not a vulnerability. So it's pretty ad hoc. So it's hard to give a general answer. But I think it's a field that we all need to explore. But I think it's a really good point, and it's a real problem that researchers are dealing with.
Okay, thank you for again.
Is there any questions from the floor? No? We have about 28 minutes. Well, I have a question. If the library is causing a problem, is there any users forum or any forums that are checking for security and releasing the results and libraries altogether?
I think it's no different than verifying the software for just normal user or kernel. So the same techniques can be applied to software that is ported to SGX or running inside SGX. But the problem at its roots, I think it's the same kind of problem.
Okay. And what about the performance? I understand that it's embedded in the chips and everything, but with all the E-cores and all-cores, does it have any effect on performances?
It's actually a really good point. I think I had a performance slide somewhere, but it was taken out at some point. But there is a really good metrics paper on SGX. So it measures the performance of SGX in so many different aspects. So there's a paper for that. So if you are interested, you can find that paper and read about it.
Okay.
And also regarding the library operating systems, as you can imagine, since we have all these abstractions inside the enclave now, it is actually significantly slower than, for example, if you developed by yourself. So yeah, performance is one thing that we didn't really discuss here, but I think if you're interested, there are a lot of good resources that you can read up online.
Is there any global companies that are using SGX? I believe like 6 or 7 years ago, Intel and Microsoft people came over to KISA and they gave us a seminar on SGX. And they said they were working with global companies such as Samsung and stuff. Is there any companies that are using SGX?
So in case of cloud computing platform, I think Microsoft is servicing with SGX. Some other companies chose other paths. For example, Amazon uses some kind of special hypervisor to implement similar functionalities. But besides the platforms, I think there are companies who are developing services based on SGX. So it's gaining more traction, and there are more real services that are based on SGX.
Okay, is there any other questions? If not, we are going to close about 25 minutes early so that you can have a good night events, whatever you have plans already. Again, thank you very much, Professor Lee. Let's give us a hands.
Thank you.
Well, thank you for being with us, and this concludes our tutorial 2 session for today. Thank you.